Hello. In this lecture I want to explain to you what is diffusive flow. We have convective flow, I have explained it. Convective flow is normal flow in one direction. If we look at our cell, here we have a simple hexaedral cell and we have convective flow from one side to another side, but you never really know in which direction the fluid will go. If you can imagine a jet or a turbulent flow over an area, it can happen that the flow can change the direction and can go in another direction, and this is described in our model with the so-called diffusive flow. Yeah. So, and you can imagine our meshes are not so easy, they are much more complicated. Here we have our dinosaur, and he's meshed with a tetrahedral mesh, thanks to Andrew Baker who did this work for Fluent. I really like the picture from the dinosaur, but it describes it really good that the meshes can be really complicated, and so the description of the convective flow and the description of the diffusive flow can be quite turbulent, and not only for this, also for turbulence description. And now we want to have a close look at the balances and the momentum balances in every direction. First, before we start, we have a look at the mass balance. Yeah? If you have a normal pipe or just a duct or a pipeline, and the fluid enters from one side, you can be sure, because of the mass conservation, that the same amount of fluid will also exit at the other side of the pipe. But what happens if we don't have a pipe, if we don't have a pipeline or anything like this, if we have an open space over the wing of an airplane or the air around a dinosaur? How can we describe it? The fluid can travel in one direction, here in horizontal direction. This is called the convective flow, but it can also change the direction and exits at another side of our cell. And this is described by so-called diffusive flows. And to build up a model for this behavior, to build up a balance, we can first describe our convective part of the mass balance. It's described by density times velocity, u in this direction, and derivated in both directions, so it's like a multiplication with the area. So if you have density times velocity times area where you enter, you get the mass flow. And additionally to this convective mass balance, you can have also movement of the masses in other direction of the cells, because there are no walls, it can go downwards. And this is described by the so-called diffusive term of the mass balance, and this diffusive term is described by the second derivation of our mass balance. Okay, here it is a bit simpler. We now have a look at our Navier-Stokes equation, and the mass balance, it's the balance of the mass flow, of course. But the Navier-Stokes equation is the balance of the momentum in every direction. We always have three directions, or it depends on your problem. If you have one-dimensional problem, you just formulate the Navier-Stokes equation in one direction, for example x direction. And if you have a two-dimensional problem, you formulate your Navier-Stokes equation in two directions. But more or less for our exercises, we will always have three-dimensional cases, so we have to describe the momentum balance in u direction, in v direction, and in w direction. And so we have to solve three equations, three momentum balances for this kind of problems. And here's the first one. It's a balance for u direction, and if the u direction enters our cell, of course some amount of the u direction can exit the cell at the opposite side, but it can also happen that the velocity changes its direction depending on our swirls inside the cell, and it exits other faces of the cell in another direction. And then it would be v direction or w direction. And you can describe this with our balance. We have the dynamic term for u. We have our convective term, that's the simple term of the equation. And it's just a derivation of the velocity component. And on the other side, we can have our movement at the other phases, and this is described by the second derivation of our velocity. So you see, we must make a second derivation in x direction, must make a second derivation in y direction and in z direction. And how big is this movement in all these directions? Here you have to remember the variable viscosity I introduced in a lecture before, and the viscosity describes how good or in which amount diffusion happens. Yeah? If we have high diffusion, if we have high viscosity, diffusion happens really fast, and if we have really low viscosity, the diffusion will not, the diffusive term will not be so big. Okay, and additionally, at the end of this huge equation, there is a gravity or pressure or other source or sink terms. And this more or less, this Navier-Stokes equation is a core of ANSYS CFX. That's what you have to control if you look at the solver manager. Okay, and I'll go to the next slide. This slide looks nearly the same as the slide before. We also have to describe the convection and the diffusion for the velocity in y direction, and that's the v velocity. So you can imagine that's a lot of work for the computer. We have the u velocity and have to do the balance. We have the v velocity, we have to solve the all terms for the v velocity, and additionally we even have to solve this equation system for the w velocity. So three different velocity parts. So you can imagine if we want to simulate fluid flow around our dinosaur with some millions of cells, the computer has a lot of work. Okay, and here you can see the convective, I've sampled it, convective part of the u direction, convective part goes in this direction, and the diffusive part of the u velocity has a second derivation, and it will exit the cell in a 90-degree angle to this u direction. And you can imagine the description is really simple for this hexahedral cells. You can imagine it, but go back to the mesh of the dinosaur, look at tetrahedral cells. You can imagine there's much more mathematics if the cell is somehow tilted or banded or like a triangle or looks like a triangle. We will need much more mathematical formulations. Okay, so let's have a short look, let's look a bit closer at this kind of model.